Slide 1. Atoms, Molecules, and Seawater Chemistry, Topic 04A, Part 1, Atoms and Molecules. Slide 2. In Unit 4A, we will look at the chemistry of water. We will learn a little about atoms and molecules, and how their motion and how they bond with one another, how they join together, can lead to all the characteristics and properties of the different substances and materials in the world around us. For example, we will learn why water is the universal solvent, about heat capacity and latent heat, diffusion and heat flow, and why some things are solids, some things are liquids, and some things are gases. Slide 3. Theories of matter. Last week we learned that a scientific theory explains a wide variety of observations. In other words, a theory is consistent with and thus supported by a lot of different kinds of observational evidence. Any theory of matter, of what things are made of, has to explain what we experience in the physical world around us every day. For example, a good theory needs to explain solids, liquids, and gases, why some substances are one thing and other substances are another, and why they have the properties they do. For example, solids are rigid, but liquids can flow. Liquids and gases both take on the shapes of their containers, but given the chance, a gas will expand to take up more space. Some solids bend, while others are brittle and break. If you change the temperature or pressure on a substance, you can cause it to transform. For example, if you heat a solid enough, it becomes a liquid. If you heat a liquid enough, it becomes a gas. This typically changes the density of the substance. The solid form of a substance is typically more dense than the liquid form, but there are exceptions like water. Ice has a lower density than liquid water. And heat flows from hot objects to cold ones. These are just a few of the observations of material things that any good theory of matter will need to be able to explain. Slide 4. The atomic theory of matter. People have always wondered what everything was made of. Long ago some proposed that everything was made of mixtures of 4 substances: earth, air, fire, and water. This was actually a pretty good hypothesis, because it explained many of the observations they had at the time. For example, mud is a combination of earth and water. Wood comes from plants which contain earth and water that they absorb through their roots, and fire from the sun. Plants need sunlight. Therefore, plants burn but not rock because they have an inner fire captured from the sun that can be released. There are many things that the earth, air, fire, water hypothesis cannot easily explain, like the existence of several airs, gases, that the early chemists began to isolate in the 18th century, the 1700s. This led to the revival of an old idea of some ancient Greeks that everything is made of small particles that they called atoms, which means uncuttable or unbreakable, and that the atom's motion and how they join or split determines the properties of a substance. Today we know that atoms are made of even smaller particles, and that some of these, protons and neutrons, are made of even smaller objects called quarks. In addition to the particles in atoms, there are a multitude of other particles: muons, pions, kaons, omega particles, various flavors of neutrinos, and so on. All of these particles may be in turn composed of strings of energy. However, most of the particles that we encounter on the Earth are just atoms. Interestingly, astronomers now estimate that less than 1/20th of the universe is made up of atoms and the rest is made of some other stuff. We don't know what this stuff is and call it dark matter and dark energy, because we cannot see it directly using telescopes. In this class we will study an old-fashioned, early 20th century, version of the atomic theory of matter, because we do not have time for much more. Basically, we'll be leaving out quantum mechanics. The basic idea is that everything, tables, chairs, air, you, me, orange juice, and so on, is made of atoms, particles so small that there are far more than a billion of them in a small cup of water. The properties of a substance depend upon the kinds of atoms it is made of, how the atoms join together, bond, and how the atoms are moving, fast or slow, wiggling in place or flying around. Atoms tend to join together in groups called molecules. Many everyday substances, like water, are composed of molecules. Atoms and molecules are constantly entering and leaving objects. For example, you breathe in oxygen and breathe out carbon dioxide. Plants extract carbon dioxide from the air and nutrients from the soil, and use them to build their bodies. Animals like cows eat the plants and rearrange the carbon and nutrients they eat to build their own bodies. We eat the cows, and breathe out the carbon dioxide. The nutrients are excreted. We can put them back in the soil to help plants grow. The key point here is that under most circumstances atoms are not destroyed, but reused again and again. You are literally made of different atoms than you used to be. For example, your skin is replaced about every month, and your stomach lining is replaced every few weeks. Slide 5. The structure of atoms and the electric force. The word atom means uncuttable or unbreakable. The word is meant to refer to the smallest possible piece of a fundamental substance. But by the 20th century, 1900s, scientists found that atoms are made of smaller parts. The central core of an atom called the nucleus is occupied by particles known as protons and neutrons. Protons and neutrons have just about the same weight, but protons have a positive, plus, electrical charge whereas neutrons are electrically neutral. They do not get involved in electrical interactions. Thus, the nucleus has a positive electrical charge. Electrically negative, minus, particles called electrons orbit the nucleus. Electrons have a mass that is about 1/1000th that of protons and neutrons. In other words, electrons are much lighter than protons and neutrons and hardly affect the weight of atoms. Slide 6. The electric force holds the protons and the electrons together. There are two basic rules that the electric force follows. Two particles with different kinds of electrical charge are attracted to one another, opposites attract, and two particles with the same kind of electrical charge are repelled by, pushed away from, one another. The closer together two charges are, the stronger the electrical attraction or repulsion is. Thus, the negatively charged electrons of an atom orbit the positively charged nucleus because they are electrically attracted to it, similar to the way in which the Earth is attracted by the Sun's gravitational pull. Neutrons have no electric charge. They are not electrically attracted or repelled by positive charges or negative charges. Neutrons are not electrically attracted to protons or electrons. Neutrons are not repelled by protons or electrons. We don't see electrical attraction and repulsion very often in our everyday lives, because whenever atoms are electrically unbalanced, that is, they are a little positive or a little negative, they quickly bond with other atoms. The underlying attraction holding objects together can only be seen when we rub off some of the electrons from atoms on the surface of objects. You can think of an atom as being kind of like the solar system. The big, heavy nucleus is in the center, like the Sun, and the electrons go around the nucleus, just like the planets orbit the Sun. Gravitation attraction keeps the planets from flying off into space. Electrical attraction keeps electrons from flying away from the nucleus. And like the solar system, atoms are mainly empty space. Different kinds of atoms. Each kind of atom has a different number of protons, neutrons, and electrons. For example, the hydrogen atom has 1 proton and 1 electron, the helium atom has 2 protons and 2 electrons, the oxygen atom has 8 protons and 8 electrons, and so on. Hydrogen is just the name that we give to atoms with 1 proton, and oxygen is the name we give to a larger atom with 8 protons. Slide 7. Atoms join together, bond. You might think that atoms are happily electrically neutral, with equal numbers of positive protons and negative electrons balancing one another out, but remember, electrons are on the outside of the atom. They all are negatively charged, so they are repulsed by one another and thus spread out. As long as there is enough space for all the electrons in orbit to stay away from one another, an extra electron or two can squeeze into orbit, attracted by the positively charged nucleus. This is what often happens to a chlorine atom, Cl, making it overall a little electrically negative because it has more electrons than protons, more negatives than positives. In this case, we call it a chloride ion, Cl-. An ion is an atom which has gained or lost a few electrons, making it overall electrically negative or positive. The opposite happens to sodium atoms, Na. There is not enough space for all its electrons to fit comfortably in orbit around it. One electron often gets pushed away by the other electrons, like a puppy or kitten that gets pushed aside by its brothers and sisters when trying to drink their mother's milk. So the sodium atom loses an electron, making it an electrically positive sodium ion, Na+, because it has more protons than electrons, more positive charges than negative charges. Therefore, sodium ions are attracted to chloride ions. Remember, opposites attract, positive is attracted to negative. This attraction holds them together in what we call an ionic bond. This bond is so strong that they form salt, a solid. Solids are harder to break apart than liquids, because their atoms are held together by strong bonds. There are other kinds of bonds. As we noted above, the electrons are on the outside of the atoms. Since electrons do not stay in one place, the electrons of one atom sometimes leave a hole, revealing the positively charged nucleus of their atom to the electrons in orbit around another atom. If there is enough space, the electrons of the two atoms will try to orbit the nuclei of both atoms. The atoms are often said to share some of their electrons. In this case, the electrons act like a glue to hold both atoms together, and this leads to a strong bond between the atoms called a covalent bond. The nuclei are both positive and therefore repel one another, and the electrons also repel one another, but as long as there is enough space for the electrons to spread out in between the two nuclei, the electrons can hold the nuclei together because both nuclei are attracted to both electrons. For example, consider two hydrogen atoms. A hydrogen atom has one proton and one electron. Its electron is happy that it has a proton, but the electron is also attracted to every other proton that comes by and would like nothing better than to have two. Thus, the electron can bring two protons closer together whether they really want to or not. When atoms bond together and remain in a group, we call the group a molecule. Molecules. A molecule is formed when two or more atoms are bonded together and remain together as a group or unit. A water molecule consists of two hydrogen atoms, H, and one oxygen atom, O, hence the formula H2O. Carbon dioxide, CO2, is a molecule made up of one carbon atom, C, and two oxygen atoms. Oxygen molecules, O2, are made of two oxygen atoms, and ozone molecules, O3, are made of three oxygen atoms. Salt is a compound, not a molecule, because the sodium and chloride ions are attracted, bonded, to all their neighbors. In other words, salt is not made up of sodium and chlorine pairs, molecules, which are then bonded together. Slide 8. Bonds between molecules versus bonds between atoms. Bonds between atoms are typically stronger than the bonds between molecules. For example, salt is a solid at room temperature. The sodium and chlorine atoms in a salt crystal are directly bonded to one another by strong bonds. On the other hand, water is a liquid at room temperature. It flows, it moves. Water molecules can move around, change places, because weaker bonds hold them together. The weaker bonds are more easily broken, and when a weak bond breaks, the molecules can move apart. The bonds between the atoms in a molecule are typically stronger than the bonds between molecules. So the hydrogen atoms and oxygen atom of a water molecule are strongly bonded together, much more so than the weak bonds that hold water molecules together in liquid water. Slide 9. Water molecules and hydrogen bonds. The hydrogen atoms are not symmetrically distributed about the central oxygen atom, but are offset to one side. In other words, the hydrogen atoms are on one side of the water molecule, forming a V shape. The large oxygen nucleus, 8 protons, exerts a stronger electrical pull on the electrons than the hydrogen nuclei, 1 proton each, so the hydrogen atom's electrons spend more time near the oxygen nucleus than their own nuclei. As a result, the water molecule has a positive, plus, side and a negative, minus, side, negative by the oxygen nucleus where there are extra electrons, and positive by the hydrogen nuclei, where there is a lack of electrons to balance out the nuclei's positive charge. H2O is therefore a dipolar molecule, a two-sided molecule. The dipolar, two-sided, nature of water molecules leads to many of the special characteristics of water. Since water molecules are both positive and negative at the same time, they are attracted to everything, whether positive or negative. Their positive side is even attracted to electrically neutral atoms whose outside is covered by electrically negative electrons. Thus, water molecules commonly form bonds with other substances, bonds we call hydrogen bonds because many substances with hydrogen also exhibit this kind of bonding. Slide 10. Hydrogen bonds are stronger than other kinds of bonds that form between molecules, but weaker than the bonds between the atoms in molecules. In other words, hydrogen bonds are weaker than the covalent bonds that hold oxygen and hydrogen together in water molecules and the ionic bonds that hold salt atoms together. What makes water special is that it forms unusually strong bonds for a molecule, especially for a small, light molecule. For example, oxygen molecules consist of two, covalently bonded oxygen atoms, O2. At room temperature, water molecules form a liquid but oxygen molecules form a gas, because water molecules are more strongly bonded together by their hydrogen bonds, making water more solid. On the other hand, at room temperature salt is a solid and water is a liquid, because the ionic bonds between salt atoms are stronger than the hydrogen bonds between water molecules. Slide 11. Before moving on, I feel the need to explain why two hydrogen atoms are on one side of a water molecule because this is crucial to explain why water is dipolar. Similarly, I want to connect what we learned about atoms in this unit to the previous unit, Unit 2b, in which we learned a little bit about radioactivity and nuclear fusion. If these explanations do not make sense, that is okay. It is not important for the course and you will not be tested on it. That being said, here we go. Why two hydrogen atoms are on one side of a water molecule rather than on opposite sides. The hydrogen atoms are on one side together because of the amount of space available in orbit around the oxygen atom. There is enough space for 4 electrons in the outer orbit. No matter how you arrange 2 items out of 4 items symmetrically around a sphere, they are always next to one another. Technically there is room in orbit for 8 electrons because 2 electrons with opposite spin can occupy the same place in an orbit, but we don't have the time or space to explain how that reduces to 4. Slide 12. Why atoms do not blow themselves apart, most of the time. The protons in the nucleus of an atom experience a very strong electrical repulsion, because they are all positive and very close to one another. The protons and neutrons in a nucleus are held together by another force of nature called the strong nuclear force. The strong nuclear force is stronger than the very strong electrical repulsion the protons in the nucleus feel for one another. Hence its name, the strong nuclear force. The strong nuclear force is only strong over tiny distances. If a proton in a nucleus gets just a little bit outside the nucleus as it moves around, if it gets far enough away from the other protons and neutrons in its nucleus, the electrical force will be stronger than the strong nuclear force, and the proton will fly out at enormous speeds because of the strong repulsion. This is more likely to happen if the nucleus of an atom is too big. You can think of the nuclei of radioactive substances as being too big and particles flying out as a result. Note that if a nucleus loses protons, it becomes another kind of atom. For example, uranium becomes lead. I mention this because this process is at the heart of the way we measure the age of rocks and the Earth, what we called radiometric dating in the last unit, Unit 2b. We also learned in Unit 2b that atoms join together to become larger atoms inside stars. To undergo nuclear fusion, the nuclei of 2 atoms fuse and become one larger nucleus. We can see now why the tremendous temperatures and pressures in stars are needed for fusion to happen. These extreme conditions are needed to force protons to come close enough together despite of the strong electrical repulsion they feel, close enough for the strong nuclear force to be able to hold them together.